So, solutions, chapter 11, let's get going. Solutions, okay, first of all, we got to learn our terms. First of all, of course, if you remember, a solution is a homogeneous mixture. We can have all types of solutions. We can have gases and gases, liquid and gases, solids and liquids, all kinds of things. So we have a homogeneous mixture, meaning they are not chemically combined, meaning I can physically separate them. One of the things we need to add to this thing is to say that within a solution you have the solute, which is what's being dissolved, and it will be present mostly in the lesser amount, what's being dissolved. And then we have the solvent, and it's what's doing the dissolving, or what it's dissolved in. Okay. Now, water is considered to be the universal solvent because so many different things dissolve in it. For instance, water is polar, so it will dissolve polar things, but it'll also dissolve ionic things. And we're going to talk about those interactions as we go through this. A saturated solution, if you remember from Chem 1, is a solution that contains the maximum amount of solute that will dissolve under that given set of conditions. If it is a saturated solution, it is a dynamic equilibrium, okay, with any excess undissolved solute present, usually down the bottom of the container. So basically, when you're in a dynamic equilibrium for a saturated solution, you have particles that are dissolving and recrystallizing at equal rates. An unsaturated solution is a solution that contains less than the maximum amount of solute. So it's less than the maximum amount, meaning I could still dissolve some more, okay? A supersaturated solution is a solution that has more than it should, and it's prepared at an elevated temperature and then slowly cooled, okay? It contains more than it should. It's very unstable, and usually the addition of a seed crystal will cause all of that excess solute to crystallize out, and then what it would leave behind is a saturated solution. The best example of a supersaturated solution is that's how they make rock candy. And you can do that at home with sugar and water. Usually it's about 2 to 1 or 3 to 1 sugar dissolved in boiling water, and then you let it cool and recrystallize. You can put either a string with the seed crystal or a stick. You can also add some extracts to make flavors. Like you could put lemon extract and you could have lemon rock candy or almond or root beer flavored or something like that. So if you are looking for something fun to do, I'd challenge you to make some rock candy at home. So here we have the saturated, unsaturated, and supersaturated solution. So those are just some pictorials you see in this one. It's still dissolving, so it can keep adding. Here, the way that we know that it's saturated is that no more dissolves. A very good example of that is iced tea at a restaurant. If they bring it to you already cold, you put a bunch of sugar in there, you stir it up, and you think, oh, that doesn't taste very sweet. And then you look down at the bottom and you got a layer of sugar. That's because you have reached the saturation point at that temperature. Okay. A supersaturated solution, supersaturated solution, say that 3 times fast, is where you can grow the bigger crystals and they recrystallize because you heated it up, dissolved more than you should, and then cooled it back down. Again, we said this earlier, that the saturated solution is at equilibrium. So we're dissolving and recrystallizing at the same size, and that can show you that on that particulate level. Same thing here, just showing you how if you make a saturated solution, you cool it slowly, add a seed crystal, and then the difference of what it should have been will fall back out and recrystallize. So the units of concentration, this is something that's changed in the AP over the last couple of years. We used to have to know molarity, molality, and now you just have to know molarity. And we've already done that when we did solution stoichiometry, but of course it's moles of solute per liter of solution, and we're going to need to know how to do those again And then, of course, mole fraction, which is something we struggled a little bit with, is the ratio of the number of moles of a given over total number of moles. Okay, it's part over whole without the percentage. So here is an example. Hydrogen sulfide gas has a solubility of 0.385 grams per 100 milliliters of water. Calculate the mole fractions of both the solute and the solvent in a saturated solution of hydrogen sulfide in water under these conditions. So let's see how we would do that. Assume 100 milliliters of solution, because they didn't give us that, so it makes our life easier. And we're going to assume that the density is 1 gram per milliliter for water, because the volume of H2S gas is going to be negligible. So we can assume that. So that means we have 100 grams of water, okay? And we have 0.385 grams of hydrogen sulfide gas. So we're going to divide by the molar mass of hydrogen sulfide, and we get 0.0113. Then we are going to take that 100 grams and divide by the molar mass of water, which is 18.02, and we get 5.55 moles of water. Then for hydrogen sulfide, the mole fraction would be the moles of hydrogen sulfide divided by the total number of moles. And so we just add those two together, and we get 0.00203. And then for water, we would take the 5.5, divide it by the total, and we get 0.998. So energy, anytime we're doing these, we're going to have some energy changes. So whether or not a solute dissolves in a solvent depends on the strengths of 3 different types of attractions. You're going to need to know this and be able to explain it, as well as the change in entropy of the system. But we're going to do entropy next semester, so don't worry about it this time. So first of all is the attraction of the solute particles for each other. Second is the attraction of the solvent particles for each other. And then thirdly is the attraction of the solute for the solvent. Okay, so these 3 attractions added up together will give you the overall heat of solution. So here is a particulate view. Again, be able to draw this of a sodium chloride being dissolved in water. Okay, and then be able to make sure when you're drawing it, and we've done this a couple of times, so you should be good with this by now, but make sure when you draw the water surrounding that you have the positive side surrounding the negative side of the ion, the positive side of water, and then when we have the sodium, we have the negative side of water surrounding the positive sodium. Also, be sure you draw the size difference. Sodium is smaller because it's a cation, so make sure you draw it smaller. Like dissolves like is what we used to say, and it is a general understanding, but do not use that on an AP exam. Do not say like dissolves like. Let's do that. Do not, Okay, that's for your general understanding, but you cannot say that, okay? We're going to talk about the attractions for the solvents to the solutes, okay? And we're going to talk about intermolecular forces between them. If they're stronger in the solute, then between the particles you won't get dissolving. So do not say this, but understand and then that like does dissolve like, but you have to know why, not just say it. So do not say it, okay? So water dissolves many salts because of the strong ion-dipole attraction. I believe we said that wrong when we did one of the things. We said ion-hydrogen bonding, and that's not true. So it's ion to dipole, okay? And so water forms with the ions, and it's very similar to the strength of the bonds between the ions themselves, okay? The same salts are insoluble in hexane, okay? So ionic salts would not dissolve in hexane because the weak London dispersion forces of their ions in the hexane would not form with the attractions of the ions. Okay, sorry about the pause. No, you probably didn't notice it, but I had to pause, so I'm not sure where I was. Same salts, okay. Same salts are insoluble in hexane because the weak LDF forces forces their ions could form with this nonpolar solvent are much weaker than the attraction. Okay, so oil does not dissolve in water. because the LDF dipole forces are much weaker than the hydrogen bonding. So there's the forces between oil and water are not strong enough to break up the forces for hydrogen bonding so that it could surround the oil particles. Solubilities of alcohols in water. As the hydrocarbon portion of the alcohol increases in length, the alcohol becomes less soluble. So let's look at, say, ethanol. And ethanol looks, it's only a 2-carbon chain, so it's CC, and then the OH is here. Okay? And so got hydrogens here, here, and here. So it will dissolve readily in water. Okay? But let's say I had something like, let's go with hexanol. Okay? Which would have a 6-carbon chain. So it would be carbon, 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 1, 2, 3, 4, 5, carbon, and then has the OH. And of course we have the appropriate hydrogens around here. And as you see, as that chain got longer, because the majority of that chain is now nonpolar in these kind of ends, it will become less soluble in water and more soluble, let's say, if hexane were the solvent. Okay? So longer the chain of alcohols, the less soluble it is in water. So the heats of solution, remember we said it was the attraction for the solvent to the solvent, the attraction of the solvent, a solute to the solute, and then of course the attraction for each other. So we can have these delta H of solutions. They can be positive, which would be endothermic, of course, just like before on delta H, or they could be negative. Okay, so let's talk about that. So first step is breaking up the solute, which is going to be endothermic, and it's where the solute is expanding. It's going to be very high in ionic and polar solutes because they're stronger bonds. Okay, it's going to be high in water because you've got hydrogen bonding. It's going to be, of course, high in ionic because they're ionic and they're stronger bonds. And it's going to be very low in nonpolar solutes because of the only thing that's acting upon those solutes is the LDFs. Okay, so your delta H of solute here is going to be equal to the negative delta H of the lattice energy. And that's because lattice energy is negative. Negative times a negative is going to be positive, so your breaking of solute is going to be positive, which is endothermic. And I realize I'm talking very fast, and I apologize for that. Step 2 is breaking up the solvent. Okay, also going to be endothermic. We call that expanding the solvent. Again, high in polar solvents, low in nonpolar solvents. Okay, notice here we're not saying anything about ionics because ionics are not going to be your solvent because they're generally solids. Okay. Step 3 is the interaction of the solute and the solvent. And this is going to be exothermic, or delta H is negative. Okay? It's going to be very high in negative, or it's going to be a high negative in a polar-polar, okay, interaction, and it's going to be a low negative in the rest. Okay? So that is the enthalpy of hydration is going to be more negative for small ions, okay, and it's going to be and for also highly charged. So it's going to be more negative for small ions and highly charged. So in other words, if I had a sodium plus and I had aluminum 3 plus, okay, so this is going to be, whoops, this is going to be higher because first of all it's small, because it lost 3 electrons, and it's highly charged. So that enthalpy of hydration for that aluminum would be higher than for the sodium. So here we have a particulate view. Remember, that's going to be important on the AP exam. Step 1 is where you expand the solute, so that's delta H1. Step 2 is when you expand the solvent, that's delta H2. And then step 3 is when they interact, and that's going to be delta H3. So it looks like that at the bottom when you put it all together. Delta H of solution is equal to 1 plus 2 plus 3. Most heats of solutions are going to be positive, endothermic. Okay, the reason that is the case is the solute dissolves is usually increasing the disorder, which is entropy, which again we haven't talked about that, but that makes the process thermodynamically favorable. The solution process involves two factors, change in heat and change in entropy, and their relative sizes determine whether a solvent dissolves a solute. Okay? So some of the factors affecting solubility is the molecular structure. Okay? So you have, for instance, you have fat-soluble vitamins, vitamins A, D, E, and K, and they're nonpolar. So they're going to be stored in the fat because fat is nonpolar. Okay? Water-soluble vitamins such as B and C are polar, and they're not stored. They must be consumed regularly. Vitamin C, of course, is from citrus fruits and things like that, and if you consume too much of that, you literally pee it out. Okay? If you've ever taken a vitamin that has a ultra high amount of vitamin C in it, it'll actually, if it's way more than you need and you pee it out, your urine will actually be like fluorescent yellow. It's kind of startling. And then, of course, you have hydrophobic, and of course phobic is fearing, so it's nonpolar, and then you had your hydrophilic, which is water-loving, meaning it's going to be attracted to the polar and the nonpolar. Pressure effects only the solubility of a gas. Okay, so the solubility, let's put only gas up here, so we know that pressure is only on gas. So it affects the higher the pressure, the higher the solubility. Okay, it's a direct relationship. Pressure has very little effect on liquids and solids, so we're just going to talk about that for the gases. That brings us to something called Henry's law, which states that the amount of gas dissolved in a solution is directly proportional to the pressure above the gas. Okay, so think about a Coke or a Sprite or Dr. Pepper and that sound that it makes when you open it. It makes that psh sound. And what that is there is a layer of gas that they put pressure on to keep the carbon dioxide dissolved in the soda. Okay, and so when you are opening that soda, that's what you're releasing, is that pressure that's above it. And of course the pressure is directly proportional to the amount of carbon dioxide that's dissolved in it. That's why when you open that Coke, it starts to go flat, because you've released that pressure. So here's an example of, as I push the piston in, I'm getting more and more of the gas particles going into the solution. Okay, and of course when I release the pressure, then I start having some of those gas particles that were dissolved come back out of solution. Henry's law is best obeyed for dilute solutions of gases, and of course it's gases that don't dissociate or react with the solvent. For instance, carbonated, we're going to go back to the soda because it's the easiest thing to think about. The CO2, remember, is a nonpolar molecule, and so it's not going to have an interaction with the polar molecule of mostly the water that's in there. Okay, of course, there's also phosphoric acid in there as well, also, which would be ionic. So the CO2 would not react with that solvent, so it's going to be best obeyed. That's why we have to put pressure on it to get it to go into solution. Temperature effects, the amount of solute that will dissolve usually, not always, usually will increase with increasing temperatures. Sometimes it will decrease. Okay, so you got to look at a solubility curve for that, or solubility chart. Solubility generally increases the temperature if the solution is endothermic. So if I have an endothermic heat of solution and I increase my temperature, then generally I would be able to increase the amount of solid being dissolved. Okay. If the solution process is exothermic, then remember, go back to treating heat as a product or reactant. If it's exothermic and I add heat, it's going to reverse it, and it's going to say no, it doesn't dissolve as much. It's going to have the opposite effect. Okay, so here is our solubility curve. We did this back in Chem 1. When we look at a solubility, we're always usually talking about per 100 grams of water. And so, of course, sugar we see goes significantly up. That's how we're able to make rock candy. or even how we're able to make sweet tea, because we heat it up, dissolve the sugar, and then cool it back down in core. And of course, if I were to heat sugar up and dissolve it at, like this looks like about 50 degrees, and I dissolved the 260 right here, and then I cooled it back down to say 10 degrees down here, the difference right here between 260 and 180 would be how many crystals of sugar that I could form. So if you notice on that chart, potassium hydroxide, sodium hydroxide, and sodium sulfate are three compounds that actually become less soluble as the temperature rises. And that's explained by Le Chatelier's principle, which we talked about in Chem 1, but we'll talk about it when we get to equilibrium. I will tell you that these are all very exothermic, okay? Sodium hydroxide, when I make solutions of that, it produces a ton of heat. It gets really, really hot, okay? And so that's an exothermic solution. So as I heat up the water, it's going to dissolve less because the temperature is rising, okay? The solubility, and we don't say always that much in chemistry, but the solubility of a gas in a liquid always decreases with increasing temperature. Always. And we don't say always very often in chemistry, so make sure you remember that, okay? That's why it's very dangerous if our waterways get too warm, because the amount of dissolved oxygen that the marine life utilizes is decreased. And so you can literally have fish suffocate if the water's too warm because they don't have enough dissolved oxygen to take in. So here's an example of gases always decreasing their solubility as the temperature increases. Vapor pressure lowering, while the presence of a volatile solute, meaning more volatile than the solvent, increases the vapor pressure, and of course increased vapor pressure means it's more likely to become a gas. If we were to add a non-volatile solute, it actually lowers the vapor pressure, and so the solvent is less likely to become a gas. Okay, so basically the non-volatile solute dilutes the solution, so there are fewer of the solute molecules at the surface to escape to become a gas. And so here's an example of that. And here's an example of the non-volatile inhibiting. So now when I have this right here at the surface, that's all I have right here to escape is the particles, okay? But now when I add a non-volatile, I have less of those particles at the surface, so less are escaping. So it decreases the vapor pressure. Liquid to liquid solutions, solutions in which they're both a liquid are volatile, and the liquids are volatile. So, sorry, oops, didn't hit the thing that I wanted to write. They do not behave ideally. Okay, so both solute and solvent contribute to the vapor pressure. If the solute is more volatile, then the vapor pressure of the solution is higher. Okay, which makes sense. So here's our vapor pressure in the solution. So now we added something that is more volatile, and so it's going to have more particles escaping to a gas phase. All right, colloids. Okay, sorry about that, another interruption. Colloids are, remember from when we did types of matter, they are a heterogeneous mixture. Sorry, I almost said it backwards. A heterogeneous mixtures, and they're like basically those medium-sized particles that don't settle out like in a suspension, but they're too big to be a solution, and so they're dispersed throughout the colloid. We call the colloidal the dispersion phase. That's going to be basically the version of solvent is and then the dispersed phase is going to be your particles. They're usually about between 1 and 1,000 nanometers, and because of their small size, the colloids have actually a very large surface area. The particles stay suspended because of the electrostatic repulsions. Okay, if you're to heat it, coagulation occurs. It's where it like sticks together. and then, or by the addition of an electrolyte, which neutralizes those ion layers. Interestingly enough, they can be separated by filtration. Types of things include foams, aerosols, emulsions, and sols, or various types of colloidal dispersions. Fog is an example of, which we've had a lot of fog lately, is an example of a colloid where you have the water molecules suspended in the air. Okay, and that is the Tyndall effect, and that's why you don't drive with your brights on during foggy night, because it scatters the light and sends it back to you. So to distinguish between a suspension or a true solution, or a colloid and a true solution, you pass a beam of light, and if it's scattered and you can see the light, then it's a colloid. If it's not, you can't see it, then it's a solution. And we talked about that in Chem 1. Brownian motion is a characteristic movement in which the particles change speed and directions. And it's a very erratic, and it's because the solvent molecules are colliding with the colloidal particles, okay? And so they're just a random movement. And you can actually see that under a microscope. It's kind of cool. Beer's Law, this is a review because we did Beer's Law earlier in the year. That was that virtual lab I had you do on that YouTube because we ran out of time. Not ran out of time, but we had to make up some time because of the hurricane. Remember, that's where you can take the solution concentration, and if you're measuring the intensity of the color, you can create a calibration curve, and then you can test unknowns to see what their absorbance is, and then you can see what their concentration is based on that. So remember, A was for absorbance, which is measured. The little a is your molar absorptivity factor, which is how much light will be absorbed, and that's usually going to be given to you. And then the symbol B is the path length of your colorimeter or spectrometer. Generally it's 1 centimeters, but it can be different. And then of course C is your concentration measured in molarity. So here is our calibration curve that we can look at, and then if we were to look something up and say, oh, we had a unknown, then we can look at its absorbance and figure out what its concentration is. And there's an example. This is old school. I don't even know if we have these. We had those in my old school, and they have been around for 500 years, I swear. They're really old. These are the veneer. We do have those up in the cabinet. We just didn't have time because of the hurricane. That was something that we could do and make up time. All right, so we have some questions here that we're going to go through real quick to get our minds thinking in AP style. So I'm going to let you read through that. Actually, what I'd like you to do, I'd like you to pause the video here, and you try to figure out the reasons, maybe even jot down, and then restart the video, and then see if you get those answers right. Okay? Again, this is what you put into it. And there's the explanation. So you might want to pause again so you can read that explanation and make sure you understand it. Continuing on with that same question, here's some more. Pause it, try to figure it out. Draw that Lewis diagram. Again, might want to pause this as you write down these explanations or make sure you understand them. And that's the end. All right, I'll see you in class tomorrow.